Time for some conclusions about what we saw in our lab and how does what we saw in our lab situation apply itself to the real world. Now, what I need you to do as you view this presentation is follow along, write down the conclusions as they're presented in order to get your done stamp. First of all, let's look at some final results, and your results might be different than mine in terms of the numbers, but the pattern should be the same. We had something like this, where we had our sand in our water started off at some temperature, and you should have seen that the sand actually got a little bit hotter than the water. The sand changed temperature more than the water did, even though they were sitting underneath the same lamp. Now, the same thing happened on the cool down side. We had this starting temperature from where they finished heating up, and we let them cool down for 15 minutes. And what you should have seen was that the sand cooled down a lot more than the water. So the change in the temperature for the sand was a lot greater than for the water. That's what you should have seen. Your numbers might be different, but the pattern should still be the same. Sand changed temperatures more, whether it was heating up or cooling down, than did the water. So here's our first big conclusion. This is what I wanted you to see from this activity, is that water does not heat up and cool down as much as sand. And the sand is going to be an example for the land out there in the real world. And of course, water is the example for parts of our planet that are covered by water. This is the big idea that we're going to apply to real world situations, is that water doesn't heat up as much or cool down as much as sand. So let's look at a real world situation. Most of you have been to the beach, and you know that when you go walking across the sand at the beach, man, that sand can be hot, burning up your feet because it's sitting out here in this nice bright sunshine here at the beach. Sunlight hits on the sand and sand gets really super hot. Well, then what do? You go and you jump in the water, and you'll notice the water, even though it's sitting under the same sunlight, tends to be a lot cooler. And this is an application of what we see, that even though they're sitting in the same sunlight, the land changes temperatures a lot more. It gets really, really hot, and the water does not. Now, what happens at night? If you've ever walked on the beach at night, you'll notice the opposite effect, that the sand will feel cool at night. So as soon as the sun goes down, man, that sand starts to lose its energy, starts to cool down. But if you get in the water at night, it's going to have about the same temperature as it did during the day, because it just doesn't heat up and cool down that much. This leads to our topic of specific heat. Specific heat is the amount of energy it takes to change something's temperature. And this is specific to a material, like sand versus water. Each material has a specific heat or a specific energy that it takes to change its temperatures. Some things take a lot of energy, some things do not. Well, why do different things heat up differently? I want you to think about two different things here. We've got a shot put over here, and we've got a beach ball over here. And certainly the beach ball is going to be a lot easier to get moving than a shot put. Well, remember that temperature is all about the movement of stuff and how they're rubbing back and forth and causing friction. So something like this right here isn't going to take as much energy to get moving faster and then therefore raise its temperature, as opposed to something like a shot put. Man, it's going to take a lot of energy to get a shot put moving fast. So every item, every material has its own specific heat or specific amount of energy that it takes to raise its temperature. Water has a very high specific heat. It takes a lot of energy to make water hot. And you know that you put a pot of water on the stove, it takes a while for it to get boiling. Things like air and the ground, they have very low specific heats. They change temperature very easily. And you've experienced this before. You're outside on a cold morning, and as soon as the sun comes up, the air around you can feel starting to get hot. So air has a fairly low specific heat. It heats up and cools down pretty quickly, pretty easily. Now, how does this impact the real world around us?
Back there behind me is the Pacific Ocean. Now, the Pacific Ocean is very, very large. It's very, very deep. It has a lot of water in it. And we know that water doesn't change temperatures very easily. It's very slow to heat up and it is slow to cool down. So places that are near water do the same. If you're along the coast, you don't get as hot or as cold as other places that are away from the water. Well, I went down there this morning and I took the temperature. It's July 25th, and the temperature of that ocean is 53 degrees. That's not very warm. Even though the sun has been shining all summer, there's too much water out there for it to ever get really, really warm. That means that this town back there in the fog, Fort Bragg, California, is never going to get really hot, even in the end of summer. The high temperature while I've been here this week has been about 60, 65 degrees. Even though it's land, and land can heat up fairly easily, it's too close to this water, which stays cool. So that means the land up and down the California coast stays fairly cool in the summertime because that water never gets really hot. On the flip side, in the wintertime, that water doesn't change too much. It won't get pretty much below 50 degrees. So that means the places along the coast in California also don't get exceptionally cold in the wintertime. And this is very much true in places up and down the Pacific coast where the Pacific Ocean's temperature stays pretty much the same year round. So the temperatures up and down the California, Oregon, and Washington coast don't change much from summer to winter. Back there behind me is the Pacific Ocean. Now the Pacific Ocean is very, very large.
And islands like Hawaii, which are way out here in the middle of the Pacific Ocean and just surrounded by water, don't change temperature that much. You'll notice here the average high in Hawaii in July is 87. In January, it's 81. So because we have so much water out here, and that water just doesn't change temperatures, and it's out in the middle of all this water in the Pacific Ocean, basically Hawaii has the same temperatures year-round.
So here I am at the airport in Honolulu, Hawaii. Hawaii, being an island surrounded by water close to the equator, means that the temperatures here don't change that much. It never really gets that hot, never really gets that cold. And one real good example of how constant the temperature is how they design the airport. You notice here behind me, there are no windows. A good portion of the airport in Honolulu is just open to the outside because it never really gets hot and it never really gets cold, so you don't really need an air conditioner or a heater. So a lot of your buildings, like your hotels and your airports and such, are just left to the open air because the temperature really never gets that hot or that cold, and it's because it is surrounded by water and close to the equator.
Jamaica, an island out here in the middle of the Caribbean, is another real good example. Because it's surrounded by water, it never gets real hot, never gets really cold. A lot of places are just open. A lot of restaurants, if you see like this, are just out in the open. This big fancy hotel, an all-inclusive resort, there were no windows on the check-in lobby. It's just open to the outside because the air never really gets very hot and it never gets very cold because surrounded by water, water never gets really hot or really cold. The same can also be true for rainforests and swamps. Any place where there's going to be a lot of water, well, water doesn't heat up and cool down. So places that are wet tend to have very moderate temperatures. They don't get really hot and really cold easily. Now, on the opposite side, a place like a desert where it is exceptionally dry, well, that means it can get really hot and it can get really cold. In Death Valley National Park, you can actually die of heat exhaustion or heat stroke in the day, and you could freeze to death at night. Well, how hot can it get there? You can get up to about 121 degrees on this particular day that I was there, and that wasn't even a record temperature. 121 degrees. How can it get that hot? Well, because it is so dry there, and really dry things heat up really easily. So Death Valley can get really, really super hot. Like I said, this was not a record temperature day. It was very hot. That's the hottest temperature I've ever experienced. And just as a little side note, just for fun, I decided to go on a run that day, and it was totally, totally miserable. Now, let's look at Lincoln, Kansas, or Lincoln, Nebraska, right out here in the middle of our country. Well, that's about as far from the water as you can get in our country, which means it is surrounded by land, which means it can get really hot and really cold. It changes temperatures really easily, just like the sand in our lab. The average high in Lincoln, Nebraska in the summertime is 88. That's about what we are here in Atlanta. It gets really hot in the summer. But in the wintertime, it can also get down to an average high of 32. So it's really hot in the summer and it's really cold in the winter, and that's because it's really far from the water. Coldfoot, Alaska. Alaska is a really big state, and out there in the middle of the state where you can get really far away from the water, you can get exceptionally cold. The town of Coldfoot has had temperatures down as low as about negative 80 degrees because they're so far from the water, just surrounded by land, they can get super cold. When I was there this past Christmas, I actually experienced a temperature of negative 35, which you can't get that cold if you're close to the water because the water won't get that cold, and it'll help keep you a little bit warmer. So, the application summary that I want you to take out of this. First of all, locations near the ocean do not change temperature easily. That's like islands or places along the coastline. If you're really close to water, you don't get really hot and you don't get really cold that easily. 2, wet places, swamps and rainforests, same thing. If you got a lot of water in your environment, you're not going to change temperature very easily. 3, if you're way far away from the water, your temperatures can go up and down quite easily, places like in the middle of our country. And finally, any place that's dry, in other words, it doesn't have any water for whatever reason, will be able to get very, very hot and very cold, just like the sand in our lab did today. So now what I want you to do is I want you to take a look at that sheet that had the 6 maps on there or 8 maps on there of different locations in the United States. I want you to go through and try to answer those questions based on what we saw in our lab today. So apply what we learned about water and sand under the heat lamp to these different locations that we see around our country. So you're going to pause this presentation at this time and go through and try to answer them for yourselves. And then I'm going to go through and answer them for you, and you can check your understanding. So hopefully you've gone through and you have made your guesses. You've tried to explain, at least in your head, the answers to these questions. You notice these are explain type questions. These are not necessarily just multiple choice type answers. So which one of these 2 circled cities do you think will change temperature more? Which is going to be able to get hotter and colder? Well, remember that the farther away you are from the water, the more you can change temperature. So Santa Fe here, which is away from the coast, is going to be able to get hotter and colder. It's going to change temperatures a lot more than Los Angeles. Los Angeles, remember, is on the coast of California. Coastal cities of California have pretty much the same temperatures all year round. Once again, which one of these 2 cities is going to change more? Well, that's certainly going to be Cheyenne, Wyoming here, because it's way far away from the water. Down here in Florida, Miami. Miami's temperatures just don't change that much. It's pretty much always the same temperature in Miami because they're surrounded by water that does not get super hot or super cold very easily. Between these two, San Francisco and Topeka, Kansas, it's going to be Topeka, Kansas is going to be colder in the wintertime. Now look how that question was phrased, colder in the winter. So one of these two cities can get really hot in the summer and then get really cold in the winter. And that's going to be the one far away from the coast. That's going to be Topeka. San Francisco isn't going to change much throughout the year because it's right on the coast. It's not going to get really hot in the summer. It's not going to get really cold in the winter. Topeka, on the other hand, is going to get really cold in the winter because it's far away from the water. Which one of these two cities do you think will be hotter in summer? So hotter in summer means you're further away from the water and you're surrounded by land, which can get hotter. That's going to be Louisville, Kentucky, because it's further away from the water than the city of Norfolk, which is right on the coast. Now, which one of these will be colder in winter? The one that's going to be colder is the one that's going to be further away from the coast. Well, Jacksonville is right on the water, so it's going to stay pretty much the same. Austin, Texas is going to get colder in the winter than Jacksonville because it's farther away from the water. Now, which one of these two? This one gets a little tricky here because now we're looking at two cities that are both far away from the water. And it's not like we're going to measure with a ruler and see that Vail, oh, maybe Vail is a little bit closer to the coast. That's not how this works. You're either on the coast or you're not. So both of these are away from the water. So which one do we think will be colder in the winter? Well, it's hard to tell from this map. Let's look at some data for these two locations. You see they're very close to one another, hour and a half, 2 hours drive tops. In January, Denver's temperature is about 49 for an average, but Vail is 29. Well, look at these two. They're next door neighbors to one another, but yet Vail is a lot colder than Denver. Now let's look at summertime. Well, Denver in the summertime is 92 and Vail is 77. So it doesn't matter if it was summer or winter, Vail seems to be colder than Denver. It's always colder. Well, this is not something that can be explained with proximity to water because they're both away from the water. But we can't forget about what we have already learned in terms of what determines a place's temperature, and that's elevation. Notice that Vail is way up higher in the mountains, and we can tell that on a physical map here. So Vail, because it's way up here in the mountains, is always going to have colder temperatures than Denver. And they're both going to change a lot from summer to winter because they're both really far away from the coast.